Trig compound angles. So in our last video we had proved that cos of A minus B and cos of A plus B, and we had already previously done cos squared A plus sine squared A equals 1, sine formula and cosine formula. So today what we want to look at then are 6, 7, 8, 9, 10, 11, 12, 13, oh no, not 13, sorry. We're going to stop at 12. And that might seem like a lot of proofs in one video, but these are all very, very short proofs. As I said, the long proof is our cos of A minus B. So as we said yesterday, the only way I can prove any of these formulas is using the information that precedes the one that we're trying to prove. I can't use anything after. So we're going to start with 7 today, and we're going to get sine of A plus B. I want to show that it's equal to sine A cos B plus cos A sine B. And that means I can use anything before 7 to prove that. Okay, so where are we going to start? Well, we proved yesterday that cos of A minus B is equal to cos A cos B plus sine A sine B. And we want to look at how can I change this into sine A cos B plus cos A sine B. So let's first of all look, what do we want to keep? So I want to keep the plus sign, I want to keep the cos B, and I want to keep the sine B. So the only thing I need to change then is sine and cos. So I want cos to turn into sine, and I want sine to turn into cos. So you might remember in yesterday's video that I showed you a way of doing that. And the way of doing that is by taking the angle A and letting it equal 90 degrees minus A. So I don't want to change the letter, I just want to change the trig. So watch what happens when we do that. That's going to become cos. Instead of A, I'm now going to put 90 degrees minus A, and then minus B. And that equals cos, and instead of A, I'm going to put 90 minus A, cos B, plus sine 90 minus A times sine B. And on the left-hand side there, if I take out minus 1 as being common, that leaves me with A plus B. And cos of 90 minus A is sine A. Sine 90 minus A, is cos A. And then on the left-hand side, just to finish off, cos of 90 minus an angle is sine of that angle. Now we're done. So if I want to change from sine to cos or cos to sine, we always let the angle equal 90 minus A. So in other words, if I put dot, 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 dot down here, remember this is not in our maths tables. If I have sine A, that's equal to cos 90 minus A. And if I have cos A, well, that's sine 90 minus A. So I'm able to change from sine to cos or cos to sine. Okay, so next one. Okay, so we're going to try and prove now that sine of A minus B is equal to sine A cos B minus cos A sine B. So I have just proved sine of A plus B. And if I go to my list, 7 comes before 8, which means I can use 7. I don't have to prove it all over again. I can take it as being fact now that sine of A plus B is equal to sine A cos B plus cos A sine B. So again, let's look at what we want to keep and what we want to get rid of. Well, I want to keep the sine A cos A, and I want to keep the sine A cos B and keep the cos A sine B. The only thing I need to change here is the sign. So you can see it's minus, here it's plus, minus, and plus. So when I only want to change the sign, what I do is I take the angle and I let it equal to the negative angle. So B, and I'm going to replace it with a minus B, because it is the B that has the negative sign here on the left-hand side. So therefore, that's going to become sine of A minus B is equal to sine A cos of minus B plus cos A sine of minus B. And of course, if we go to our maths tables, page 13, well, we can see top right-hand corner here, we have cos of a negative angle is equal to cos of that angle. So that's just going to become sine A cos B. And sine of a negative angle is equal to minus sine of that angle. So again, be very careful here that you're putting in brackets around the two of those, because you're multiplying, not subtracting. So therefore that's going to become sine of A minus B is equal to sine A cos B. Sine A cos B, and cos A times minus sine B is minus cos A cos sine B. Cos A sine B. Okay, so QED. Another one done. So again, really short theorems today. So if I go back to my list again, let me just delete all these. So we have done 1, we've done 2, 3, 4, 5, we've just done 7 and 8. So the next one on our list is tan of A plus B. So again, I can use everything before 9, but I can't use anything after 9 to prove it. Okay, so we have to prove that tan of A plus B is equal to tan A plus tan B over 1 minus tan A times tan B. So where we're actually going to start with here for this one is that tan theta is equal to sine theta over cos theta. And again, this is in our maths tables, and it's the top left here. Tan A equals sine A over cos A. Okay. So therefore, what that means is if I take the left-hand side there of what it is I'm trying to prove, and I have tan of A plus B, well then that can be written as sine of A plus B over cos of A plus B. And if I go back to my list, well, we've already done sine of A plus B, it's theorem 7, and we've already done cos of A plus B, it's 5. Or we can go to our maths tables, which is page 14, 15, and we will be able to actually find those formulas. So in our exam, we can see here that we would be looking at these two here on the right-hand side of my screen here, but we have cos of A plus B and sine of A plus B. So again, you can see they come before our tan of A plus B, which means I can use them in my proof. Okay, so what is tan or sine of A plus B? Well, it's sine A cos B plus cos A sine B. And that's all over cos of A plus B, which is cos A cos B minus sine A sine B. So here is what we have to figure out is where to go next in order to end up with tan A plus tan B over 1 minus tan A tan B. So if we look at the top of the screen here, the biggest hint I can give you is this 1. Right? How can we get 1 down here in that position? Because at the moment we have a cos A cos B, but I need that to become 1. So the only way I can get 1 there is by dividing everything by cos A cos B, because cos A cos B divided by cos A cos B will give me 1. So that's now going to become sine A cos B all over cos A cos B plus cos A sine B over cos A cos B divided by cos A cos B over cos A cos B minus sine A sine B over cos A cos B. And then we just need to simplify. So cos A divided by cos A is 1, cos B divided by cos B is 1. Okay, well, what's sine A over cos A on the top line there? If I put brackets between those, well, cos B goes into cos B once, and sine A over cos A is tan A. Cos A will go into cos A, and then we're left with sine B over cos B, which is tan B. We have 1 minus, and then if I just put brackets around those, because they're again multiplied by each other, would give me sine A over cos A, which is tan A tan B. So the biggest hint is always that 1 to tell us what to do. It's the key to solving that problem. So theorem 10 then is to prove that tan of A minus B is equal to tan A minus tan B over 1 plus tan A tan B. So again, we can use everything before theorem 10 in order to prove this. So we've literally just proved that tan of A plus B is equal to tan A plus tan B all over 1 minus tan A tan B. But I wouldn't be able to use theorem 10 to prove theorem 9. It's really important. Order is really important here. So again, if I compare theorem 9 to this one, you can see that everything is the same except for the sign. So it's plus, it's a minus, it's a plus, minus, plus, minus. So therefore, if the only thing that's different is the sign, well, it's the same as we've seen before. We let B equal minus B. So wherever there's a B, we're just going to change it to a negative angle. So that's going to be tan of A minus B is equal to tan A plus tan of minus B all over 1 minus tan A times tan of minus B. And again, if we go to our tables for the negative angles and we check for tan, so again up here we can see tan of A minus tan of the negative angle A is equal to minus tan of that angle. So in other words, we have tan A minus B is equal to tan A, and then that's going to become minus tan B over 1 minus tan A times minus tan of B. And of course, we're multiplying there on the bottom line, not subtracting. And then lo and behold, we end up with tan A minus tan B over 1 plus tan A tan B. So to change the sign, we replace with B equals minus B. Okay, so if we go back to the first page there, then what we can see is we have just done seven, 8, 9, we've done 10. And we're now going to look at what we call the double angle formula. So we're going to do 6, and we're going to do 11, and we're going to do, not 12, sorry. 6, 11, and 14. And we'll leave 12 and 13 and 15 and 16 then to next week. So these are our double angle formulas. So I just actually bring that down. So the ones up to this point have been compound angles, and these are double angle formula. So theorem 6 is prove that cos 2a is equal to cos squared a minus sine squared a. And where we're going to start with that, again, if I go back to theorem 6, we can see we're here. So I can only use anything that has gone before theorem 6. So obviously the one we have that we're going to start with is cos of a plus b. So theorem 5. So we know that cos of a plus b is equal to cos a, cos b, minus sine a, sine b. Now if we're looking at our tables, because we want to know which formula comes before which, we can see here that cos of 2a is here. So therefore anything that is above that can be used in this proof. Okay. So therefore, what I'm going to do with this one is I need to basically only have A in my answer. So if I only have A in my answer, that means all these B's have to go. So this is a really easy proof because we literally just replace the angle B with A. So that becomes cos of A plus A is equal to cos A minus sine A, sine A. And then we're done, because A plus A is 2A. And cos A by cos A is cos squared A. And sine A by sine A is sine squared A. Lovely. Now the two that tend to spin off this one, which aren't in your maths tables, and come in very, very useful when solving equations, is where I write cos 2a in terms of only cos or in terms of only sine. So it's not listed in our proofs, it's not listed in our tables. So this is an aside or a note. So if I was asked to hence show that cos 2a can be written as 2 cos squared a minus 1. Well then I can only use my tables to solve this. And the most commonly used identity is cos squared a plus sine squared a equals 1. So I have to start with what I've just shown there. So cos squared a minus sine squared a. I don't want sine squared in my answer, but I know that sine squared a plus cos squared a is equal to 1. Therefore, I can say sine squared a is equal to 1 minus cos squared a. So that means wherever there's a sine squared a, I put it in brackets, 1 minus cos squared a. And then I get rid of the brackets. And that's cos squared a minus 1 plus cos squared a is equal to 2 cos squared a minus 1. And the second variation is where we're asked to write cos 2a in terms of only sine. In other words, show that it's equal to 1 minus 2 sine squared a. And our approach is exactly the same. We start with cos 2a. And in our tables, it tells us that that is equal to cos squared a minus sine squared a. And I say, but sine squared a plus cos squared a is equal to 1. And therefore, cos squared a is equal to 1 minus sine squared a. And if you can't remember that, we can find it on page 13 in our tables. So this one here. Okay. So therefore, subbing in, we end up with cos 2a is equal to 1 minus sine squared a instead of cos squared a minus sine squared a, which gives us cos 2a equals 1 minus 2 sine squared a. Done. So next we're going to prove theorem 11. So it's the second of our double angles. And again, this is page 14 in your table, so you can see it here. Sine 2a is equal to 2 sine a cos a. So all of these are going to be really useful when we're solving our trig equations at the end of the chapter. So we're going to start with what comes before that, which is sine of a plus b. And we know that sine of a plus b, if we look at page 14, is equal to sine a cos b plus cos a sine b. And same as in the previous one, we don't want any b's in our answer. So that means we need to change those to an a. So we're going to let b equal a. So we get sine a plus a is equal to sine a cos a plus cos a sine a. And therefore, you can see we end up with sine 2a. And sine a cos a is the same as cos a sine a. So that means there are two of them. So it's 2 sine a cos a. And the last proof of today, I promise. All very short proofs, but a lot all the same. The last one is going to be our tan 2a. So again, this one here is tan 2a is equal to 2 tan a, 1 minus tan squared a. So again, anything above that can be used for our proof. So again, we're going to start with, same as for cos 2a and sine 2a, we're going to start with tan of a plus b is equal to tan a plus tan b over 1 minus tan a tan b. And exactly the same as the previous ones, we don't want any b in our answer, so wherever there's a b, we're going to replace that with a. And therefore that becomes tan a plus a is equal to tan a plus tan a over 1 minus tan a times tan a. And that's it, done. Tan 2a is equal to, tan a plus tan a is 2 tan a. And tan a times tan a is tan squared a. So we finish with our proofs for today.